All right, guys, in the last video, we talked about how to fill the Eudiometer the proper way. So before we actually start the lab, I'm going to have to prepare my beaker. That beaker is going to have some water in it, at least 2/3 full, if not more. And then I'm going to grab a Eudiometer, and the Eudiometer is going to have some hydrochloric acid here in the very bottom. And just no rhyme or reason. The lab directions, again, will tell you how much HCl to pour in there. As long as you're close, this reaction is going to work. And then we are going to slowly trickle water on top of that HCl down the sides of the Eudiometer until we overfill that Eudiometer. All right, so now I've got this prepped Eudiometer. How on earth am I going to do something with it? Because I need to turn this upside down, but I also need to make sure that when I do this, that hydrochloric acid is going to come in contact with my metal, and in this case that's magnesium, for the reaction to take place. All right, so I'm going to erase this diagram because this is what we had last. And now I'm going to draw the Eudiometer opening here. So this is me looking down the Eudiometer. This is the opening of it. And what's going to happen is I'm going to take my magnesium strip, right? I've cut a piece of magnesium strip, and I'm going to pinwheel it first, all right? And when I pinwheel it, I don't want to do too tight, but I need it to be to a point where it's going to be somewhat stable. So don't feel like you really have to crunch it, because sooner or later we're going to have to actually thread a piece of string through this pinwheel. All right, so when I say the pinwheel, what I mean is that once this magnesium strip has been rolled on top of itself, like a little Debbie cake, a little Swiss Miss Debbie cake, we're going to wheel, roll until we roll that up into a coil. And that magnesium strip, then I'm going to take a piece of thread and I'm going to thread through the center of that magnesium strip. So that way I'm not really kind of attaching it really at this moment, but I've ran it through the middle. The coil is going to allow that magnesium strip to stay in place until this reaction actually comes in contact with it. I can tie a knot around this if I want. That is not a big deal. I actually suggest it. And then once you do that, that pinwheel magnesium strip is then going to be positioned right here on the opening of the Eudiometer, and that string is going to come out to the side and get attached with a piece of tape, and then it will come off to this side and it will get attached with a piece of tape there. I know it sounds like, oh my gosh, this is rigging it up, but I promise you it will work. There's no issue here at all. All right, so my magnesium coil at this moment is going to be on the end of the Eudiometer. And now I need to take my finger and I need to flip that Eudiometer upside down. So my piece of magnesium coil is going to be here in the bottom. And that, yet again, remember, has been taped on the sides so that way it doesn't go anywhere. I probably have a knot tied into that magnesium coil so that way it doesn't go anywhere. And then I've got this HCl up here at the very top that I have mixed in, well, hopefully not mixed at this point, but HCl up here on the top that has some water in it, right? So this very dense HCl is going to slowly go down the Eudiometer, and you can actually sit there and watch it happen. It'll be very wavy. You'll be able to track where it goes and how fast it goes. But sooner or later, that acid, as it's mixing with this water, it's still acidic. It's going to hit this magnesium coil, and all of a sudden, ta-da! The magic begins to happen. So Mg and HCl, a single replacement reaction happens, giving us magnesium chloride and H2 as a product. So I start to see bloop, 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 little gas bubbles that form in my Eudiometer, and that gas will get trapped up at the very top. And then what will happen is that, just like we said, that gas takes up room. And sooner or later, that gas is going to push that water out of the eudiometer to a point where it's eventually going to stop. And that's when the reaction comes to an end, right? So I've captured all of this H2 now up here in the top part of the eudiometer. This is where our H2 has went, right here. And that H2, I'll be able to read that out because I'll know where that mark hits, and that eudiometer has graduated markings on it in 0.1 mils most of the time, or 0.2s, and I'll be able to record the volume of hydrogen gas that I have captured during this lab experiment. Okay? All right, so all of this, though, has to take place. Keep in mind, it's got to take place in a beaker, and that beaker's got to be at least 2/3. It's got to be submerged. So that eudiometer has to be submerged in that water. So at least 2/3, if not more, on the inside of that beaker. So that way, the whole entire eudiometer does not pour out. I want the H2 to push it out. And if I do not submerge that eudiometer in the water, well, it's all just going to dump out all at one time, and it doesn't make any sense. All right. Okay, so sooner or later, this reaction is going to stop. I quit collecting gas, and now I'm going to get a readout for milliliters of H2. All right, so if I go back to the lab procedure, let's take a look at what it says. Number 4, fill the beaker with water. Number 5, pour 10 to 12 mils of diluted HCl into the eudiometer. Then slowly fill with tap water, don't mix it, and allow the water to travel down the walls of the eudiometer. Number 6, coil 1 piece of magnesium ribbon. Using a string, thread it through the center, tie a knot around it. Number 7, attach the one of the magnesium coils to the open end of the eudiometer and use tape to secure that thread and that piece of metal in place. Number 8, ensure that the liquid level in the eudiometer is to the top. Place the finger over the open end, invert it, and submerge it in the beaker. You should have no air bubbles at all, period. Number 9, clamp the eudiometer in place. The HCl, and that can be done with a burette clamp. That's all that this is. It is the size of a burette. So a burette clamp makes great, kind of nice, convenient clamp here for us to use. HCl will eventually fall and react with the magnesium coil and cause bubbles. Number 10, when the gas evolution stops, make the following measurements. So A says the gas volume in milliliter in the eudiometer. All right, so I've got that. That's a direct readout. Nothing to do fancy-wise there. Next up, B, the temperature of the water in the beaker. All right, so here's my beaker. I'm probably going to have a thermometer here because I need the temperature at some moment in time. That temperature of the water is going to be very important because what we have just done here is a setup, and that setup is called collection over water. So I have collected gas over water because it's been submerged in water. There's a specific type of calculation that we have to do here. We'll talk about that a little bit later. But this is what really general chemistry and some of the high school science classes leave out, because collection over water is the most common way that we collect gases in a lab. And these calculations are left out because it looks a little crazy and it's complicated maybe looking, and it's just all about the basics of the gas laws, which is great, but collection over water is important. All right, so I need the temperature of that water, and that temperature is going to be provided to me in Celsius. But there's an issue here, and we'll talk about that in just a second. Next up is C, the barometric pressure. All right, so when I calculate the pressure, I'm not going to actually calculate it at all. So when I look at pressure, I'm going to measure this in terms of torr. That's going to be the unit that we're going to measure with. And we've got vernier barometers that will tell us what the pressure of the room is. So I do not need an old school barometer hanging on a wall to get this measurement with at all. The only thing that I need is a nice little convenient instrument for me to plug in, turn on, and it's just going to pop out a number and it's going to say this is your pressure. But you need to keep in mind you want that pressure to be recorded in torr. That is how we're going to kind of keep track of all of these values. Eventually they're going to have to get converted, but we're going to have to keep track of all these values in the meantime. Next up, D, it says measure the distance. Measure the distance between the water level in the eudiometer and the water level in the beaker. And notice it says it's probably going to be better to measure that in centimeters, but you eventually need to convert that over to millimeter for this thing to work. All right, so what that is talking about is it wants me to take a ruler. I know. And it wants me to line up that ruler at the level of water in the eudiometer, and it wants me to go down to the level of where that water is at in the beaker. So I'm going to have to use my ruler in order to measure that distance. That distance, based on the rulers that we have in the lab, is probably going to be centimeters. If we've got one that measures millimeter, though, then go for it. But that centimeter measurement, we do want to convert that into millimeters at some point in time. All right. So I've got A, which is the gas volume at the top of the eudiometer. I've got B, which is the temperature of the water in the beaker. I've got C, which is my barometric pressure. And I've got D, which is the distance between the water level in the eudiometer and the water level in the beaker. Number 11, it says correct the barometric pressure for water pressure and the level difference in millimeters, mercury, or torr. And it says this will require a reference chart. So this is one of those reference tables that I talked about just a few minutes ago. And this reference table is giving us a value that we're going to have in our calculation. So remember I said that the temperature of the water is going to be very important. So the temperature of the water in this very brief table, we've got bigger ones that we'll use, but in this very brief table is going to hang around room temp. So a little bit below room temperature and a little bit above. So below 20 and above 25. And you'll go through and you'll find what temperature your water is going to be at. So let's say that we measured our temperature of the water and it's 26 degrees. All right, so here's 26. And then right to the side, it says 25.2. 25.2 is the partial pressure of water in millimeters of mercury. All right, so that's very important for our values because that is one of the reasons that we've got to convert things over to mmHg in order for this calculation to work out. But this pressure of water based on the temperature is going to come from a reference table. All right, so here is our lab directions. And now we can start filling in missing pieces of the puzzle little bits at a time. So let's say that my magnesium strip weighed 0.080 grams. So that is what I would put there. The next line item says the hydrogen volume, but this is in terms of liter. So let's pretend like I collected 13.6 milliliters. I don't know. Let's just kind of say that's what happened. Here, let me make it easy. Let me make it really easy. Let me get rid of the 13.6 and let me just change this over to a 15. So I've captured 15 milliliters of hydrogen gas in the eudiometer. I started at 0. It pushed the water down until the 15 milliliter mark. So this wants liter. So I'm going to divide this by 1,000 in order to get liter. So 15 divided by 1,000. All right, so 0.15 liter is going to go there. Next up, it says, well, what's the temperature of the water? We talked about that just minutes ago. So what's the temperature of the water that you measure with your thermometer? So let's say that this is 26 degrees Celsius. Then the next line item says, okay, well, what is that in terms of Kelvin? All right, so Kelvin is going to be required because many of our gas laws are based with Kelvin as a unit of temperature. They do not use Fahrenheit. They do not use Celsius. So we've measured it using our thermometer using Celsius, but in order to convert it to Kelvin, I need to take 273.15 and I add the Celsius temperature readout to that number, and then that will give me a Kelvin value here. So 273.15, and then it's going to add in this case, 26. All right. So 273.15 plus 26. Whoop, sorry. And there we go. 299.15. So that's going to go in for Kelvin. We're eventually probably going to have to use that in some form or fashion. That's why the table's asking me for it. So 299.15 Kelvin. Next up is the barometric pressure in terms of torr. So barometric pressure in terms of torr, just a few minutes ago, we talked about what this is going to call for, and that is going to be in reference to my vernier barometer. So I'm going to pull that out, plug it up to the LabQuest, allow it to measure the pressure of the room, because that's where the lab data took place, and it's going to pop me out a number in terms of torr. So let's say, I'm just going to make it up, that this value is 769.13. So 769.13. Next up is the water vapor pressure. So the reason is because we're collecting over water, and there's water in the eudiometer, and that water is putting pressure onto the basin of my container because I'm collecting it over water. So water has a certain amount of pressure that is going to be related to it just because it is present and it is there. And that is where this table comes from. So the table that I showed you just a few seconds ago, folks, something that looks like this, that is where that value is going to come from. So if we measure 26 degrees with our thermometer, then my water vapor pressure is 25.2 millimeters of mercury. So that is a constant, and that constant depends on the temperature of the water at that moment in time when the lab data took place. So 25.2 is what I would use in this kind of spreadsheet. So vapor, water, pressure, 25.2. Again, yours could be different depending on the temperature of your readings when you took them. Next up says level difference of water. Well, we just talked about that as well. So that is the level of water in my eudiometer and the level of water in the beaker. I want to take a big metering or meter stick, and I want to measure the number of millimeters or centimeters that is there. All right, so if I do that, let's say I'm going to make up my number. My level difference here in terms of millimeters of water. So I use my meter stick. Maybe I measured it in centimeters. I don't know, but maybe I did. And then I'm going to go into millimeter by moving the decimal again, right? Or multiplying by the appropriate number. So when I go to millimeters, let's say this value, I don't know, I'm just going to make it up. All right, so we'll use 138, right? So that is what I got from my meter stick, and I converted it over from centimeter to millimeter, maybe, but 138 millimeters is the difference between the water level in the eudiometer and the water level in the beaker. All right, so next up is the level difference in terms of millimeters of mercury. So I don't really care about millimeters of water because it's a different unit. My pressure can be recorded in torr, and torr is actually equal to millimeters of mercury. They are the same number. So for instance, 760 torr is 760 millimeters of mercury. So now you see where we're going with this. We have measured pressure in terms of torr, and I have a value from a reference table in terms of torr. but I've got millimeters of water in the eudiometer that I'm measuring. So we got to convert that over so that way everything can be apples and apples and oranges and oranges. So in order to do that, I'm going to divide by 13.6. The reason is that this is the density of mercury, 13.6, customized for this reaction to take place, or this conversion to take place smoothly in one step. So I'm going to take my calculator and I am going to go in and I'm going to say, okay, well, my water difference is 138 millimeters. So I'm going to divide that by 13.6. And this will convert my millimeter of water into millimeter of mercury instead. So I'm going to get a number. I'm just going to record 2 digits after the decimal. So 10.15. All right. So 10.15 is going to be the level difference millimeter mercury wise. Next up, the reason that we did all of this is because we need a corrected pressure in terms of torr. So what this means is that I've got a pressure of the room, and the pressure of the room is 769.13, right? Then I've got water vapor pressure in terms of a table. That was also torr. That presence of that water is contributing to the overall pressure that's going to be happening from the reaction. So what I need to do here is subtract the pressure that is directed in this equation, in this setup, due to water. So I'm going to subtract 25.2 from that value. I don't care about water. I don't care about the pressure that the water is putting onto the system. I only care about the gas in the eudiometer and nothing more. And that's why we subtract that water value. Next up, the level difference of the water from the eudiometer and the beaker. We converted that over into millimeters of water, but then we converted it into millimeters of mercury. That millimeters of mercury is also the level difference in terms of torr, because we just said 1 torr is 1 mmHg. Those units mean the same numbers. So now I can subtract my level difference of mmHg, and that was 10.15. That is how I correct for the actual pressure that is going to be on the system because of my hydrogen gas only. So 769.13, I'm subtracting the water contribution, and now I'm subtracting the correction for the water level because it's sitting up a little bit higher than the rest of the water in the beaker down below. So we got to account for that extra. And by subtracting those numbers, I'm going to get a corrected pressure for torr. And this is 733.78. So 733.78 is my corrected pressure. Next up, it says, okay, well, a lot of our gas laws that we work with, they actually don't use torr. They use ATM instead. So over to the side, 760 torr is equal to 1 ATM. So this is another conversion that I'm going to have to do on the side of this thing in order to figure out what is this value in terms of atmospheres, ATMs, not torrs, because atmospheres is what's going to be needed for the eventually equation that we need to plug into this thing. All right. So in order to do that, it's a simple conversion. I'm going to take whatever value that I get, 733.78 in this case, and I'm going to divide by 760. And the reason is because this is 733.78 torr, right? And then we'll kind of do this step by step to make dimensional analysis hawks happy. So divide that over 1. The next step, torr on the top, torr on the bottom. There's 760 torr in 1 ATM. So I'm going to take 733.78 and then I divide by 760. All right, so I'm going to bring that calculator onto the screen. 733.78 divided by 760, and I get 0.9655 for an ATM value. I'm just going to keep everything. It's 4 digits, not a big deal. So 0.9655 is going to go in for my corrected pressure. Okay, so next up is the number of moles of H2. Oh gosh. Now, how on earth do we get that, right? Mole is a quantity. I've got volume of the gas, but how do I get quantity of the mass? I mean, I'm going to have to sit there and count every single little molecule of H2 that has been captured in the eudiometer? No, of course not. That's crazy. Who would do that? So there's a nice little equation that we can use in order for us to calculate what this value is supposed to be. The number of moles of H2. All right, this is going to go back to general chemistry. And what will happen here is that we need to use an equation called the ideal gas law. And the ideal gas law looks like that. PV equals N, R, and T. Oh, maybe now all of the other data in the table is going to start to make sense, because all of that was preempting you a little bit in getting your ducks in a row so that way your units will match out the proper way. So PV equals nRT. This is called the ideal gas law. So anytime we have a gas under ideal circumstances, and that will never happen, never, ever, ever. So ideal gas laws are great, and they work theory, but they're not perfect, because no gases are perfect in a lab environment. We're always doing something to it that doesn't quite make sense. But either way, it'll be good enough, all right? So the ideal gas law, the P is going to stand for pressure, and the V is going to stand for volume. Well, pressure of what? Pressure of the gas. Oh, the hydrogen gas that I collected. Ding, 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 ding. You got it. And that pressure has a required unit of ATM. That's why we had you to convert. And then the volume of that is the volume of the gas that you collected. Oh, the eudiometer displays the volume. The volume, though, is in terms of milliliter. I know, but guess what? The ideal gas law needs the unit of liter. But no big deal, because look at your data sheet up here at the top. We had you convert that to a liter, and that's why. See, we're always one step ahead, and I want you to remember that. All right, next up is N, and N in the ideal gas law is the number of moles. And ta-da! That's what we need to calculate. So that means that in this equation, I will be solving for N, because N is the number of moles of hydrogen gas, and N is the number of moles of hydrogen gas that the data table is going to want. So N is what I'm solving for. That's my variable. The R is something that we call the rate constant. And the rate constant is a constant. That means that that is a number, and that number is going to be given to you in the lab directions. And the only thing that I have to do is take that number and plug it in to R to make this thing work. All right, so if it's found in the lab instructions, where on earth is it going to be? Well, let's take a look here. All right, so if I scroll back up, number 10. When the gas evolution stops, make the following measurements. So number 11 says correct for the barometric pressure for the water vapor pressure and the level difference. And this will require a reference chart. And that's just what really I showed you just a few minutes ago. Picking out the appropriate temperature of the water, subtracting that mmHg, or really torr, from the total pressure, as well as the corrected water level difference. Number 12 says complete the calculation chart, PV equals nRT, and this is what we were just now discussing, the R value. And the R value is important because it really locks into place all of the units that we have for the equation. So based on that 0.08206, now keep in mind, R can come in many different versions and many different ways. But the one that we're using for the equation that's given to you in the procedure is going to be in terms of liter and atmospheres of pressure then the moles of substance, which is what we're after, and K for Kelvin. So that is exactly why we needed those units to be converted very early on in our reference chart and our data table, so that way we can prepare it for this ideal gas equation, as the R is going to be provided to you in those units. So 0.08206. All right, so R is 0.08206. And then T is, of course, our temperature, and our temperature needs to be in units of Kelvin. All right, so that is going to set the stage for the main calculation at the end of this lab experiment and our data sheet. So based on the made-up lab data that we did here, I need to calculate the number of moles of H2. Okay, so PV equals nRT, and I'm just going to clear, beep, there you go. All right, so PV equals nRT. I know that the R constant is 0. And yet again, right up here at the top, 0.8206. All right, so 0.8206. That's my R value. The N is something that I need to calculate because that's the number of moles of hydrogen gas that was collected. The T is the temperature, but that temperature has to be in Kelvin. So that's why we made that conversion here in the data sheet. There's my temp, and it's in Kelvin. So 299.15 is what I need to use there. All right, so 299.15. Over on the left-hand side is the volume of hydrogen that was collected. So it looks like the volume of hydrogen in this particular trial run with made-up numbers is 0.015 liters, because that's what the R value wants. So 0.0, whoopsie daisy. Let me redo that. 0.015 liter. And then the corrected pressure here has to be in terms of ATM. So we did the pressure of the room minus the pressure from the water minus the level difference of the water that had been converted to mmHg, otherwise known as torr, so 10.15. And we got a corrected pressure of 733. We divided by 760 in order to get a corrected pressure in ATMs, because that is what the R value wants. So 0.9655 is what needs to go into that equation. 9655. All right, so if I use my calculator, and let's just do this in baby steps to keep everything nice and simple and clean. I'm going to multiply the two numbers on the left-hand side first, 9655, and multiply by 0.015. So I'm going to get a number of 0.01448. All right, so 0.01448 equals N times, and I'm going to multiply these two numbers here together, right? Again, baby steps. That's the key here, to not mess up on the math. So 0.08206, and then I'm going to multiply by 299.15. Then I hit enter. Ta-da! 24.548. All right. So 24.548. To solve for n, I'm then going to divide each side. And I'm going to divide each side by 24.548. Order of operations, a little bit of algebra. That cancels these out. So I'm going to take 0.01448 and I'm going to divide that by 24.548, and then I'm going to get a really tiny number because we didn't collect maybe a lot of gas, right? And this would make sense. I mean, moles is like 6.022 times 10 to the 23rd atoms or molecules. Huge. So based on this equation, it looks like on all of these values, I collected really 0.000, because that's e to the negative 4 out here at the very end. 5899. All right, so 0.000, and then my calculation was 5899. So 5899. So this is going to represent the number of moles of hydrogen gas that was collected from the equation based on our magnesium coil strip mass, because that was really the limiting reactant. When the magnesium strip just kind of disappeared and fully dissolved and fully reacted, the reaction stops. It's not going to produce any more H2 gas at all. All right, so this is going to be how I determine the number of moles of H2. So the number of moles of H2, that blank is going to come from my PV equals nRT equation, and I solve for N, which is the number of moles. Next up is the number of moles of magnesium. So now I need to relate these two different things together, and that's going to be through the use of a little bit of stoichiometry. That's what we call that when we try to relate the amount of one substance to the amount of another substance. So what I'm going to do, I'm going to erase some of this on the screen. We need that number, the number of moles of H2. That needs to stay around. That's going to tell me how many moles of hydrogen gas I've collected, right? So I'm going to take that number and I'm going to do a little bit of dimensional analysis inversion of stoichiometry with it. So 0.0005899, and this is going to be moles of H2. So I'm going to put that over 1. In the next step, mole of H2 on top, so mole of H2 is going to go on the bottom. And I need to get this into moles. I don't know why it does that. I need to get that into moles of magnesium, because that's really the thing that we are after in this equation. So moles of magnesium. In order to do this and relate these two things together, I need to know something about the balanced chemical reaction. So it's going to be Mg and HCl is going to react together to give me MgCl2 and H2, right? The reason it's MgCl2 again is because magnesium carries a positive 2 and chloride carries a negative 1. So I need 2 chlorides in order to counterbalance that magnesium. The H2, it's diatomic. It always shows up in a couple. So if there's nothing else for it to pair with, it's going to pair it with itself. So H2 diatomic hydrogen here. And this is what I collected in the eudiometer. But this equation is not balanced. So I've got 1 magnesium on the left and I've got 1 magnesium on the right. I've got 1 hydrogen on the left, and over here I have 2 hydrogens on the right. So we need to balance these equations, and in order to do that, I'm going to write a big 2 out here in front. So that way that is 2 hydrogens on the left now and 2 hydrogens on the right. I can only add big coefficients. I cannot separate things from each other. I cannot break up compounds and relationships. That's not what I do. So I got to put big coefficients out in front. Next up, this 2 also goes with the chloride as well as it goes with the hydrogen. So I've got 2 chlorides now in total on the left, and that's okay because on the right hand side I've got 2 chlorides on the right hand side as far as my product goes. So this is a balanced chemical reaction, and the reason that we did this is because these are the values that we're going to have to plug into this step of the equation. So there is a mole of H2, and here is H2. There's no number in front, so that's understood to be a 1. And then I need moles of magnesium. So if I look at my balanced chemical equation, here is magnesium, and there's no number that we had to write in front, so that means there is a 1 in front of that value as well. So that's really all that we have to do to calculate the moles of magnesium that were required to generate this amount of hydrogen gas. It is a 1-to-1 relationship, which means that on the data sheet, whatever number I get here is also the same number for the moles of magnesium. It's a 1-to-1 based on the balanced chemical formula. Next up, the atomic weight of magnesium. All right, so this is going to be in versions of the calculated atomic weight. Because, folks, that's what this lab is all about. We are calculating the formula weight of magnesium on its own. So the way that we do that, okay, so I'm going to take my eraser and we're going to get rid of this. So now we know that not only is this the number of moles of H2, but it's also equal to the number of moles of magnesium. It is a one-to-one relationship. We just proved it. So this is the value that we're after. To calculate formula weight, keep in mind, what does that mean? If you calculated the formula weight of something, what kind of unit would you have? Gram per milliliter. No, that's density, right? Okay, well, instead of gram per mil, what unit goes at the bottom? You got it. That's going to be mole, grams per mole. All right, so what's going to happen to calculate the formula weight here? I'm going to take the mass of the magnesium coil from the very beginning that I weighed out. I think in our example, we use 0.080 grams divided by the number of moles of magnesium based on that reaction and how much hydrogen that was kind of given up and trapped in the eudiometer. That allowed me to backtrack and calculate how many moles of magnesium that we had from the very beginning. So we just calculated that number. We said it is the same exact number as the moles of hydrogen. So the only thing that's left for me to do to calculate formula weight, laboratory-wise, we are calculating formula weight that should appear on the periodic table, is I'm just going to take 0.080 divided by grams, divided by moles, 0.005899, and I hit enter, and ta-da! I get 135.616. Oh my God. So this is going to be the formula weight based on the laboratory data. And folks, I got to tell you a secret. These were made up numbers along the course of the way. I was just kind of willy-nilling it all the way through. And based on my calculation, I'm getting 135 grams per mole. I know that this is a big fat that is not right. And that's because the formula weight for the magnesium atom, or a mole of it, is 24.31 grams per mole. So I hope that when you do that calculation in the very end, when you take the mass of the magnesium that you have up here from the top, and you divide it by the number of moles of magnesium that you calculated from the equation, that you get something really close to 24.31, right? You're going to find an average atomic weight that is here. So once you get an atomic weight from that row, and then you got to do it again. So you do this twice. You're going to take the average of both of those, and that will go here. You're going to compare that to 24.31, and it wants you to calculate the error, and then it wants you to calculate the percent error. All right, so those two are very similar, slightly different, but not a big deal. So to calculate error, you're going to take your value minus 24.31 and take the absolute value of that number. So in other words, the error here is really regarded as the difference. It's the difference between your value and the accepted value, which is 24.31. Once you calculate that error, or that difference, then to calculate the percent error, you're going to take the difference that you just calculated from up above, and then you're going to divide it by 24.31, which is the accepted value from the periodic table, and then you're going to multiply it by 100 to get a percentage. So once you do that, you'll calculate a percent error. And folks, I'll go ahead and spoil it for you. These percent errors very often are way less than 5%. And in very many cases, in many semesters now, we've had people to generate percent errors that were less than 1% from the periodic table with just makeshift rulers, a little bit of thermometers and barometers, some beakers of water, and that's about it. Some tape and some string. And we're able to get that close to the formula weight of magnesium on the periodic table. All right, so that is how we complete our data chart. That's really what's going to happen here for the gas lab using the eudiometer. Keep in mind, this is called collection over water, or collected over water. And very often a calculation that's not really explained very well in general chemistry at the college level and sometimes in high school levels. But this is the prime easy motion of capturing gas from a reaction, doing some calculations with the gas that was captured, and then relating that to something on the periodic table that we've always seen all the way up to this point. Formula weight of magnesium, straight from the periodic chart, 24.31. And this is a laboratory way in order to prove that that number is what that number really is. All right, so good luck on the eudiometer, a little bit of gas laws. Really, just the only thing that we focused on was the ideal gas equation, PV equals nRT, where we need liters for volume, atmospheres for pressure. The R is a number that's a constant with proper units. The T is temperature for Kelvin, and N is the number of moles. So good luck. I don't think that you'll need luck. This works too well for you to really mess it up. And if you need help setting it up, or if you want me to demonstrate how to do it the right way for the first time, please let me know. I'll be glad to fill that thing with water. Flip, 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 flip over. And then that way you can see how to handle those eudiometers when there's real stuff that's there. All right. So good luck. If you got any questions, let me know. But otherwise, have fun with the eudiometer. Again, another piece of glassware, another lab method we haven't had a chance to talk about, and another setup that's quite odd and strange, because that's what this semester is all about. Odd and strange, just like me.